All right, so today we're going to start looking at what's known as confidence interval. So that's directly related to that plus or minus 3% that you see at the bottom of your polling data and any kind of thing you should see on TV. So first thing we're going to looking at, well, the first definition is what's known as statistical inference. So the U.S. Census, what does the U.S. Census do? But how do they do it? They literally ask every single person in the entire country. Okay, that's literally what the census is. They have to ask every single person in the entire country every 10 years. Yes.
Asking like what a census was.
Yeah. So that's what the census is. There is a lot of people, and I have a sneaking suspicion we're going to hear this in the next 4 years, that want to get rid of the census and move to a statistical inference of the population, which means instead of counting every single person, they will do a statistical analysis of areas to determine the populations. Okay. It would save a ton of money. The U.S. Census is expensive. I think it last the 2021, or actually the 2021 was rather more expensive than normal. But even the 2010 one, I think, cost almost $10 billion to do it. Because if you don't send back the actual paper that you get in the mail, which not everybody does, they hire somebody to literally go out and knock on your door. They hire people to walk the streets and talk to the people, the homeless people. They walk through the streets and talk. They have to hire a ton of people to do this. So it's rather expensive. However, it is something that is mandated in the Constitution to do, because that's how we get our apportionment, our representation, and everything else is tied to. So a statistical analysis of it would make it cheaper. However, we're going to see in this chapter and the next one how it's not exactly as accurate. Like, it doesn't get the exact number. It's an estimate of what that information is. And we can get it close, but we can't get it exact. So statistical inference is basically taking our data and inferring what's really going on based on that data. There's 3 things that we're going to look at are estimators. Actually, we're only going to look at 2 of them. The third one we're not going to do. These are known as point estimators. So an estimator is a estimate of the population parameter. So when we've seen these before, that's that X bar. That's the estimator of mean. So that is the mean that we're estimating. So it's not the actual mean of the population, we're estimating. Then we have the p hat, and that's the estimate of the proportion. So it's not necessarily the proportion of the population, it is our estimate of what we would see there. The last one is standard deviation. We are not going to be doing the standard deviation analysis part because it's actually a lot more complicated and it's a whole different set of rules and stuff for it. So if you go on to Stats 2, you will most likely be working with the chi-square and the standard deviation stuff. If not, you'll never need to know it. All right. You can finish right. Let's show it in a second. All right. What's this? I think There's the bell curve. I'm like, I'm sure we've seen this enough by this point. That's the bell curve. And then if we look at it, the line down the middle is our mean, which wasn't exactly where it was supposed to be. It's close. Okay. So this basically says that the the population mean's in the middle, and then we're going to get some number that's close to it. These are all the different possible sampling means or point estimates that we can get. Some are better than others, depending on where our data shows up. What was this called? It starts with an E. This is the empirical rule. This is the one that states within one standard deviation, we have 68% of all of our data. Within 2 standard deviations, we have 95% of all our data. Within 3 standard deviations, we have 99.7% of all of our data. So if I want to be 68% sure, I only need to look at 1 standard deviation. If I want to be 95% sure, I have to look out to 2 standard deviations. Okay, so that means my range that I'm going to have, or my interval, is going to be a little bigger, depending on how much data and stuff I look at. So, yeah. All right, this right here, very important. Everybody write this down. If you have your Z table still, write it on your Z table. If you don't have your Z table still, I think there's a few of them still over. There's a few of them over there. If you gave me your Z table on your test, which some of you did, see me and I can give it back to you. Because I know some people gave me their Z table.
The below this one, is that a standard deviation there?
It's
I can't see
it's an A.
it. Okay.
I'll explain what that means in a minute. It's not actually that important. So when we're looking at this piece right here, where it's that little A, I'll give everybody another minute to finish writing this down before I switch back to the other slide and explain to you what that means. This little table is going to save you from having to constantly look back at your Z table, because these are the numbers we're going to use pretty much exclusively from this point forward. Okay. So the problems are going to tell you how confident you want to be in your answer. So if I want 80% confidence, that's going to be my Z score. If I want 90% and so forth. If I want 95%, I want 1.96. Now, if we looked back at this right here, what was the empirical for 95%? 2 standard deviations. It's actually not exactly 2 standard deviations. It's exactly 1.96 standard deviations. So instead, for the 95%, we're going to use 1.96. It's very close, like a rounding error away from it. So that's why the empirical rule is an estimate. It's not an exact. It's close. So that'd be the 1.96, and then that would be negative 1.96 would be the 95%. What's left over at the 95%? If we took that away from 1, how much is left? Yeah, 5%, right? So if I split that in half, that means I have 2.5% on this side and 2.5% on that side. That's what that other little piece asked for, says. So if you notice, the confidence is 1 minus A. This is A. Okay. So the A is what's left over on the sides. So if we took that 5% and cut it in half, if I looked at my Z table for 2.5% or 0.025, I'd get 1.96. That's what that means. That's what I said. That piece right there is a symbol. It's not overly important. You're never going to need to use that. The numbers underneath it are your Z's that you're going to need to know. Okay? All right. So to create a confidence interval, come on. There we go. So if we know our standard deviation, and on Wednesday, you are not going to know your standard deviation. I'm going to give you a new table on Wednesday. So as long as you know your standard deviation, and the sample is drawn from a normal population that is bigger than 30, remember that 30 is that key piece of information. Those two pieces of information are going to be the things that we're going to vary on Wednesday. That's why it's kind of important to actually have those stated there. A confidence interval of the population mean is given by this formula. So there's the formula. Again, you don't necessarily need to use that. Just write down the Z is fine. It is the sample mean plus or minus Z times the standard deviation divided by the square root of n. What that's going to give you is your confidence interval. So if my value is here in the middle, I can tell how far to either side I am of that value that I would be a specific number of confidence in. Like I would be 95% confident that the actual mean is somewhere between here and here. Or I would be 80% confident that the actual mean is somewhere between there and there. So write that formula down. You need that formula. The plus or minus, you're just going to do it twice. You're going to add it and subtract it to get both directions. These are all symmetrical. So you only are finding one Z. That's how you get your positive and negative version. That's where the plus or minus comes from. It's the plus Z and the minus Z. Yes.
So is the standard deviation over the square root of n, is that multiplying the Z?
Times the Z, yeah.
Okay.
Yeah. So it's you find the Z and you multiply it by that piece.
Okay.
I always do this backwards. So this is what it would look like in Desmos. You can't do the plus or minus. You have to do it as two separate things. So you have the minus version and then the plus version. And then the four values that we're going to need to plug in. All right, let's actually do it. So we're taking a random sample of 100 cars. That has a mean weight of 425 pounds. So basically what I'm doing is I have not weighed every single engine in the world. I've weighed a random sample of 100 of them. And they've come out to be 425 pounds. That is my thing that I've done. Okay? I've taken 100 engines, I've weighed them, and they've come out to be 425 pounds. I want to construct a 80%, 90%, 95, and 99. We're going to do two of them. confidence intervals for the population mean if the standard deviation of the population is 900. So we're going to assume that the population is 900. And we're going to do, let's do the 80 and then we're going to do the 95. Let's do 80%. So my confidence interval is 80%. So on your table, which was the Z for 80%? Yeah, 1.28. Everybody able to find that in the little table you wrote down? Yeah. My N is 100. My X bar is 425. And my standard deviation is 900. All that's given to you in the problem. Now we need to do our formula. So I have 425 minus 1.28 times 900 divided by the square root of 100. And I have 425 plus 1.28, 900 divided by the square root of 100. Doing those calculations, these are the two numbers you should get. So what that means is that I am 80% confident that the actual mean of all engines is somewhere between 309.8 and 450.2 pounds. Okay. I want you to do the exact same thing, except this time you're doing 95%. So everything stays the same except for what number? Yeah. The Z is going to change. And we're going to look at 95% for this one. Huh? Yeah, you're just doing 95. What do you notice?
As the confidence interval gets larger, the range also becomes.
So what's this one saying? So the last one I was 80% confident, right? What's this one saying?
90.
I'm 95% confident. Nothing else changed in the problem, right? So if I'm now more confident that my answer is going to be correct, I'm going to have to widen the area that it's going to fall into, right? I can't be more confident and have it shrink, because if I was more confident it would be less, then I would have just been that way to begin with. So when you're looking at your confidence intervals, you'll notice that they get wider and wider depending on how confident you're going to be at it. So 80% we were between 309 and 450, 90% 276 and 573, the 95 248 and 601, and if I'm 99% confident, it's 193 to 656. So when you're looking at how to say how confident you are, it's really going to depend on how much data you have and what are you talking about. So in this case, I looked at 100 engines, right? If I had increased the 100 engines and looked at 500 engines, all those would shrink because I'm dividing by a bigger number. Okay, so that's one way to shrink the confidence interval, is to look at a bigger number. The other thing is that in most situations, 90 or 95% is all you're going to really need. The ones that really use the 99% confidence interval are your medical tests and your medical things in healthcare. They really don't go up to that 99% confidence interval because in some situations it could literally mean life and death. So they want to be absolutely sure that it's going to be in that range there. Okay. All right. So we're the manufacturer of a soccer ball. Have any of you actually blown up a soccer ball before? To the point of explosion? So for safety situations, I have to have some kind of a warning on there, right? Saying, do not blow up past this PSI. Otherwise, cause a injury. Because if you do it, as long as I have the warning on there, it's your fault, not mine. All right. So I need to make sure that I can put on that pressure thing and be confident that it's not going to blow up before that point. So they did a sample of 100 soccer balls. The population standard deviation is 13.25. The sample mean, so the 100 ones they did, the PSA necessary to pop a soccer ball was found to be 147.58 PSI. They want you to calculate the 95% confidence interval of the population mean. So find me my 95% confidence interval for this problem. So I'm 95% confident that the soccer ball's maximum PSI is somewhere between 145 basically and 150. Okay. So which PSI am I stamping on the ball? Yeah. So give me a number. What number would you stamp on the ball?
Worried about legal issues. I guess like 145.
Okay. I probably would have even gone lower and put 140.
Yeah.
A little bit more of a margin of error in there. But 145 would have been fine. It's like, no, so actually, here's a really good question. So you stamped 145. What percentage of balls do we estimate would explode less than 145? 2.5%. So that'd be 2.5 balls out of every 100. So if you sell 1 million balls, talking about what, 25,000? Okay. So you can start to see how, okay, 95% might be good for some things, but we might have wanted to go to 99% for this one. All right, so what's 99%? So everything's going to stay the same except for the Z, because I'm moving it up to 95%. %. Yeah. What was the Z?
He was 2.575.
Is it that big of a difference? Yeah. We're down to closer to 144, but not. So now, what's the chances of a ball exploding under 144 pounds of PSI? Yeah. 0.5%. So 0.5%. So if I did my 140, the chances are basically next to nothing. Okay. So you can start to see how manufacturers and people would use this type of information for it. Okay. One of the really cool things about this formula that you just looked at. So where is it? Where's the formula? This one. Is if I just looked at this piece here, if I just looked at this part right here, that's what I'm adding and subtracting to, right? So in essence, that's giving you my error. Okay. So some of the problems that we talked about last class was they wanted a within 3 pounds or within a certain percentage of where we were, right? And you had to figure out both directions. So in essence, the same thing we're doing here. We're just going the other direction. We're saying, okay, I want to be this confident. What's the error on both sides of it? So that's what that gives me, is that error. So if we solve that equation, because I'm not going to make you do the algebra a million times, this formula right here is going to tell me how many people I need to ask to get the error that I want, or how many items that I need to look at to get the error that would be acceptable. So the only thing that's different on this one is the E down the bottom. That is your error. So that is whatever the error that we're looking for is going to be. So suppose a quality control manager at a chemical company wishes to measure the average amount of cleaning fluid and the company is placing in their 12-ounce bottles. So they want to make sure that there's 12 ounces in every bottle, or at least as close to that as possible. Because if it's too low, then the customers are going to complain. And if it's too much, I'm wasting money. From previous studies, they believe the population standard deviation to be 0.3 ounces. How large of a sample must be taken in order to be 95% confident that a 12-ounce bottle is within 0.05 ounces? So, 95% confidence interval. What's my Z for that? 1.96. Now you know why I told you to write down that little table earlier, because you're going to use those numbers a lot. Basically every single problem going forward. All right, so we've got that. So I've got my Z, my standard deviation is 0.3, and my error is 0.05. So I've got 1.96 times 0.3 over 0.05 squared. When you type this in your calculator, again, I would use Desmos because Desmos is nice and it actually shows you exactly how it's written. You want to make sure you do your inside first and then square it. If you're not going to use Desmos, if you're going to use your regular your calculator on your phones, make sure you do it in pieces, because the chances of you typing it all in perfectly is very slim. So we've got, I'll flip over to Desmos in a second so you can see how I just want to type in it first. So that's what it would look like in Desmos. 1.96 times 0.03 divided by 0.05 squared. Yes.
Like with it as variables instead of.
Oh, I didn't type the variables in for this one.
Oh.
I can. It would be C times S divided by E. That would be the formula. So 138.29, so on. So the question was, how many items would I have to look at to get that error? So I've got, that's my answer when I plugged it into the formula. So what's the answer to the question? And not you. How many should I ask? Or how many bottles of cleaning fluid do I need to look at to make sure I get my error? Yes. Why? Why wouldn't I just round down? Okay, very good. You always want to round up on this, because technically if you go down, it's not 0.05 anymore. Okay? You would want it to be bigger than that, not less than that. So you always want to round up on these situations, no matter what the number is. So my answer to this question would be 139 bottles. Does it say anywhere in this problem how many bottles of chemicals this company makes? No. In the formula, does it ask for that information? No. They could make millions of bottles of fluid. I only need to look at 139 of them. Okay. You remember what I told you a while ago? It says, how many people do I need to ask in the entire country to get within 3%? That's where that number is coming from. It doesn't matter how many people in the country. It doesn't matter how it's. If I'm looking at the state of Connecticut or the entire country or the city of Hartford or the city of Norwich, I need to ask the exact same number of people because that population, that bigger number, doesn't matter in the formula for figuring out my area. Okay. The only things that matter is the standard deviation and what the error is and how confident I want to be. Yes.
What would you do in a situation where a town is smaller than that number?
I wouldn't be as confident.
So you just
You lower your confidence at that point. So. Suppose a sample of 410 randomly selected radio listeners revealed that 48 listened to WXQI. Find a 95% confidence interval for the proportion of radio listeners that listen to WXQI. Yes.
we don't have our standard deviation.
Okay.
Is that a hard set result?
Yep. So now, have we done problems like this before? This is a what type of problem? We've done two types of problems in the past few weeks. Mean problems and proportion problems. Okay. This is a proportion problem. Do they need to give me my mean and my standard deviation for proportion problems? No, we can find those. Right? Okay, so in this situation, I've got to find them. The nice thing is, everything else we've done today still stays the same. Nothing changes. So I need to find my p-hat. So I got 48 out of 410. So what proportion listens to WXQI? So my suggestion, if you're going to use Desmos like this, I would keep that as a fraction. Okay? Because then you don't have to worry about rounding and rounding errors. All right? So I would leave it as the 48 over 410. My standard deviation. What was the formula for standard deviation? The square root one. So it was P, and then 1 minus P hat over the number of people. So in this case, it'd be 48 over 410. 1 minus 48 over 410 over 410. So now the question is well, how? Oh, actually, the formula does change. Wait, hold on, does it? Oh yeah. Does change slightly. I forgot. We don't have to do the square root piece in the bottom. All right. So my formula. Yes.
What do you mean? Don't-
I'll say it because remember, and when we did the problems last class, you didn't have the over this. We had to do divided by the square root of n when we did the mean problems, but the proportion problems we did not have to do the square root of n. Same problem in this one. We're not going to have to do that square root of n underneath. I'm going to write the formula right now for you. So your formula for these. Oh, sorry. I need my confidence interval first. Is 95%. So that means my z is what? Yes. All right. So my problem for this one is going to be p hat plus or minus the ZA squared times the standard deviation. Because we've already got this whole piece there. You've already done the square root of n. Yes.
What are we getting from this?
It's giving you your confidence interval.
So solving the p hat plus or minus.
Is going to give me that same confidence interval that I was just doing for the mean. The only, if you notice, the only difference in this formula is there's no square root of n underneath. Because I've already done it here. Okay, so I don't have to do it again. Okay, so here is how I would show you that. Here's how we would do this in Desmos. 41 over was 48? Was it 48? 48. 48 over 410. My z was 1.96. And this is how I would do these problems. I would just do this. I would put the formula for standard deviation in there, so I don't have to type it again. Because remember, you're using that value there. Does that make sense? Again, you don't have to do it this way. You can easily type the equation in by pieces and get out the answers. If you're going to do it by pieces, round to at least 4 decimal places when you're doing your work. Okay? This way it just saves me all that extra work. So 48 out of 410 was about 11.7% or 0.117. So my confidence interval for this at a 95% confidence interval, my P is going to be somewhere between 0.148 and 0.086. So about 8.6% to 14.8% of the people would be listening to the radio station. So you're still doing confidence intervals. We're just looking at it in terms of a proportion instead of a mean. Do one more of those before I do. Here. All right. Yes.
Just to confirm, what we were saying last time is there's like a 95, you're 95.
We're 95% confident.
That 8.6 to 14.8% of people will be listening to that.
Correct.
Okay.
Yes. I know it's a whole lot of percents. Yeah, when you're looking at proportions, it's like we're 95% confident that 8% to 14% of the people are listening to this radio station. Yes. Yes, there's a whole lot of percentages in there. But it's the same concept. It's like, so what the radio station wanted to know was basically what percentage of people are listening to my station. You go through all your analysis and everything else, do surveys and all this other stuff, and come back and say, okay, I believe between 8% and 14% of the people are listening to your station. I will tell you right now, when you're going to go present your data, your information to the board or whoever is in charge of this, you're not saying 95%. You're just saying, I'm confident that between this and this is listening to your station. And then they're going to go to advertisers and goes, I've got 14% of the people, because they're going to always go to the high number. I got 14% of the population of this large metropolitan area listen to my station. This is how much your ads are going to cost. Okay. So that's what they're going to use that data for. All that other information, the 95%, all that stuff is going to be in the report that nobody's actually going to read. Which is how, if you remember at the very beginning, I says you can lie with statistics. Because was the answer that 14% of the people in the population listen to my radio station?
Technically true, like, right, the number's there.
Right. And that's where that thing is it could be. That is a possible thing, but 8% is also possible. So it's a matter of, it's within that margin of error that we looked at, but like that's that playing with those numbers. And that's that playing with that information. Because somebody else could say, well, 8% is. Well, that also is technically true. Just depends on which direction you want to look at, right? So that's why when you're looking at all this data and everything else, it's always important to say, okay, let me see the actual report. Because it's really nice to look at and say, okay, what was the actual numbers? What did they actually do? And you're going to get a lot more information about what they're actually talking about. And you'll see that those numbers are in there, but you'll understand a better idea of what those numbers mean, which is kind of the big goal that I want you to get out of this class. That's the goal. All right, so this one, we've talked about before, if you're doing a clinical trial for a drug thing, typically you want to do it, remember we talked about the blind studies and the double blinds, where people don't know if they're taking the drug or not, but everything is the exact same. They have the placebo there. So in this one, 500 random subjects conducted by this drug company, the percentage of patients reporting improvement when given a placebo was 37%. I want a 95% or 99% confidence interval because this is a drug study. Of what was the percentage of patients improving when just given the placebo. Remember, they're given basically a sugar pill. There's nothing in it. Yes.
Would the 37% be written as like P or P hat?
That's P hat. Because we're estimating P. P hat is the information we're given.
All right.
So my confidence interval is 99% for this because it's a drug trial. And they gave me my P hat is 0.37. Remember, change it to a decimal. So my standard deviation is 0.37 times 1 minus 0.37 over 500. Then I have 0.37 plus or minus. The Z was 2575?
Yeah.
So 2.575 times whatever your standard deviation was.
You use 4 decimals for the standard deviation.
I would. If you're going to type the number in, I would definitely use 4 decimal places for this. So 4 decimal places for your standard deviation was 0.0216. So the actual percentage of people showing improvement on the placebo would be somewhere between 0.314 and 0.426. All right. Does that make sense? Yeah. I'm sorry. Okay. Last formula. Because of the way this works with proportions, we have a little different formula for the error. So if you want to, so it's n equals z squared times p minus 1 minus p over e squared. Yes.
Still,
It is still the error, yes. All right, so remember that radio station we looked at earlier? They want a maximum error of 1% or 0.01. So if you remember, right, when we did this before, it wasn't that far back. Where was it? There it is. We were 95% confident, but the error was 8.6 to 14.8. If we're at the 0.11, that's like a 3% error on both sides. So that's a plus or minus 3% thing. They want an error of no more than 1%. So how many people are they going to have to ask or survey to figure this out? So my n equals 95%. What's my z for 95%? 1.96. And then it's 0.1171 times 1 minus 0.1171 all over 0.01 squared. Oh, I forgot to square the 1.96. what was it, 1171? So there it is set up on Desmos. So we'd have to ask 3,971 people, or 3,972 people, sorry. To get a 1% error. Yes.
How did you get the X to work? I was trying to use X as a variable on Desmos, so it just kept graphing it instead.
Don't use the graphing calculator.
Okay.
Do the scientific calculator. Because yes, if you do the graphing calculator, it likes to graph the X. At that point, use any other letter other than X and you're fine.
Yeah, I tried that.
But yeah, the scientific calculator doesn't have the graph, so it doesn't matter. All right. We're doing polling for an election. 2 candidates are running because that's all they ever care about. I want to be 95% confident that my data is going to be within 3%. So 95% there. What would my assumption be to start my polling for my percentages if I have 2 candidates? Yeah. Right. So I'm going to set my percentage to 0.50. And I want a 3% error rate. So I need to ask 1,067 people. Or 1,068 people. That's it. If I'm sure that it's something different, like 45 or 40%, notice how that number right there doesn't change by much. And actually it goes down. So that would be the maximum number of people I'd have to ask to be 95% sure that the data that I get is within 3%, which is what every poll you ever see posted says, plus or minus 3%. Yes.
So this is the rounding up to get 106.
Yeah.
That you're talking.
Yep. So 1,068 people. That's it. And that technically works for anything. Any poll, as long as it's between just 2 options, because remember, proportion's got to be a binomial experiment. So it's only got to be, can only have those 2 options there. That's all you need to ask. Craziness, huh? If I wanted 1%, I'd have to ask 9,000 people. So that's why a lot of times you'll hear that it's a statistical tie, is because the numbers that they get are within the 3%. So they're fine with it. It's not outside of the margin of error, so therefore it's a statistical tie. It's when it gets outside of that 3% that you can say somebody has an advantage over the other person. So, all right, don't leave yet. I have a question to ask you, but I want to stop this first because I don't need this in the recording.